Hey everyone, this is Shikhar Singh from MS Ramaiah University of Applied Sciences, and I'll be presenting you the paper titled Deep Learning Model for Image-Based Plant Disease Detection on Edge Devices. Plant diseases are a major threat to food security. Um, Crop diseases are responsible for major economic losses in agriculture industry worldwide. They can also have disastrous consequences for smallholder farmers whose livelihood depends on healthy crops. Monitoring crop health early are essential to reducing disease spread and facilitate effective management practices. Crop diseases are a major threat to food security, but their rapid identification remains difficult in many parts of the world due to lack of necessary infrastructure. The result of crop diseases leads to inadequate food to humans, which can lead to starvation and death in worst cases. Also, more than 80% of the agricultural production is done by smallholder farmers who can't tolerate the loss of crop yields as their livelihoods depend on it. More than 50% of the yield loss has been due to pest and diseases. And talking about India, India alone faces annual loss of approximately 50,000 crore in Indian rupees, and the smallholder farmers, which accounts to most of the Indian majority. Um, in their death toll, there has been several surveys, and we found out that 70% of the farmer suicides have been related due to loss of crops by plant diseases. So, what is the solution to it? Solution is making something which is easily accessible to the farmers of Indian origin and also to the farmers at global scale, which can be done through smartphones. Smartphones offer very novel approaches to identify diseases because of their computing power, high resolution displays, and extensive built-in set of accessories such as advanced HD cameras and GPS modules. Approach of training deep learning models on increasingly large and publicly available image datasets presents a clear path towards smartphone assisted crop disease diagnosis on a massive and global scale. The combined factor of widespread smartphone penetration equipped with cutting edge technologies can lead to a situation where disease diagnosis based on automated image recognition can be made available to an unprecedented scale. The combination of increasing global smartphone penetration and recent advances in computer vision, made possible by deep learning, has paved way for smartphone assisted disease diagnosis. And this is what we are going to do. We are using smartphones and the use of deep learning models to create an app which is very easily accessible by farmers to know the diseases that can affect their crops very easily. Our proposed solution, we are presenting the app which has the following structure. Basically, the app will have an authentication feature which will be through mobile phone, because we are assuming that farmers might not have an email address initially. But they will have a phone. That means they will have a phone number, and hence the authentication is being done through phone numbers. Um, Also, the UI features weather alerts and forecast for them to know the upcoming weather, so that they can take remedy measures accordingly. Um, Coming to the main part, our app takes an image with the metadata, as you can see here. This metadata is then sent to the backend where the images are saved and the metadata is saved to database. The other call happens to our ML model, which can be online, offline, depending upon the internet availability. If the model is offline, that is, the farmer has very less internet connection, then the classification of diseases is done based on the model that will be inbuilt with the app, and it will do the plant disease diagnosis, confidence classification, and then it will show query the database for the related preventive measures. The online model is something different. When the farmer has adequate internet access, our online model is pretty stronger than what we ship with the app. So the online model will be able to classify diseases at much more accurate scale and uh, with higher confidence scores. Then it will query the database as what I mentioned before, and then it will show the appropriate remedies and diseases that are detected by the user uh, to the user. The sequence diagram. So basically, this shows the entire flow of the app which will go. So we have the Krishi AI app engine and the Krishi AI model server, um, and the database. When the user opens the app, he encounters the interface where he is asked to authenticate using mobile number. The app engine then authenticates the user. The user then can click images to of their plant leaves, basically. This is sent as an image data to the app engine. The app engine then collects the GPS location coordinates to map the particular field, and then it is sent to the Krishi AI model. The app engine then saves the image and sends the image to the model. The model then perform image analysis and then send back the result to the Krishi AI app engine. The Krishi AI app engine then queries the database for effective remedies and preventive measures based on the disease that has been detected, and the remedies are then sent back as a list, which is then showed to the user on the UI screen. Apart from this, as I mentioned before, the user can also view weather alerts and other specific things related to a particular day. Let's say the weather content, the humidity, etc., etc. So our goals and objective. Our goal was to conduct a comprehensive literature survey on various methods for image-based plants disease detection, um, uh, so that we can, get the list of models which are very high cutting edge and provides very high accuracy when it comes to plant leaves image detection. To arrive at the design specifications of the system based on identified requirements, and to build and train various CNN models for plant disease detection and compare their performance. Other thing was to develop and deploy a web server for CNN model for inferencing, and to design an intuitive UI to develop a cross-platform mobile app based on the requirements. Goals is when we arrive, the image classification is done using convolution neural networks. For this purpose, plant village dataset has been chosen, which is being used by most of the papers that we referred to in our literature survey. Also, this plant village dataset has been made very has very large number of different species of plants with different kind of diseases. So we thought this is the best thing that we could use. Several CNN models are trained and evaluated to get most efficient and accurately trained model. Several instances of the model were also created using Docker by containerizing them, so that the server doesn't fall short of the resources. All instances were then deployed using Kubernetes, and web application was made using simple EJS and REST APIs. The mobile app was made using Flutter because Flutter is a new cutting edge tool which facilitates development in both iOS and Android in case there are users other than farmers who are using iOS apps. Results and conclusion. So this is our plant village data set. We did very heavy data augmentation. We tried random flipping left right, random flipping up down, randomly rotating uh, clockwise and counterclockwise 45 degrees. Random cutout of 64 into 64 bit augmentation was done. Resizing with padding to 288 was into 288 bits. Um, Random crop to 224 to 224 dimensions was done, and then this data set was sent to the models for training, and the results were arrived in the following manner. As you can see, the MobileNet v3 without augmentation and Inception v3 with augmentation gave the best results, but Inception v3 suits our case with augmentation. This is the chart which is being shown for training loss, and as you can see, the loss decreases for the increasing number of approaches. Inception ResNet was also trained, but Inception ResNet took quite a lot of time to um, get trained, so we didn't really go until seven epochs. We only trained it for three epochs, but as you can see, it immediately started showing very great results, but due to the time frame, we couldn't really train it much further. This chart shows the train accuracy for for the same models. Here also we can see that MobileNet V3 and Inception V3 with augmentation and MobileNet V3 without augmentation shows the best result. Um, they achieved higher accuracy at higher epochs as compared to other models. Also, we noted down the uh, data which shows the exact figures of all of these models. So as you can see here, MobileNet V3 with augmentation showed 93.7% train accuracy. Without augmentation, it shows 97.22% of accuracy. Test accuracy was being shown as 78.55%, and without augmentation was 88.44%. The train loss was 0.68 and 0.42, which was quite good. Uh, for MobileNet V3 large test, it shows a very good accuracy of 80.74% with augmentation, and without augmentation, it shows 88.25%, which is like way better than what we would have achieved by using other models. If we come to Inception V3, as it is a very heavy model as seen in the size, it showed a high accuracy of 89.17% with augmentation and 96.47% without augmentation. We also did some data visualization where we did guided grade cam analysis. In case of plant disease classification, grade cam will help us understand which part of the image does the CNN rely on for classifying the image. This will also tell us that model is actually learning relevant features from the image. Here, as we can see, the hotspots are the regions which are affected by the diseases, and we can see in GradCam analysis that the regions are being marked by the hotspot. So we know that our model is actually using the exact regions that we want it to use. And when we come to saliency maps, it also shows the exact affected regions which were being shown, which we wanted to use. So yeah, the visualization shows that the model was on the right track, and hence we could do go forward with the training. Model size comparison, as we know, is very important because we are going to ship the model with our app. So we need very lightweight model which gives very high accuracy. And from our analysis, we got to know that MobileNet V2, Inception, ResNet V2 gave the higher accuracies. When we do the model size comparison, MobileNet V2 is only of 13.7 MB, whereas the TF Lite version of MobileNet V2 is only 8.83 MB, which is very lightweight and can be shipped with the app, and it will serve as an offline model when there is very low internet connectivity. On the server side, we will host Inception ResNet V2, which has a very high size as compared to the apps that are usually shipped with the phone. So it had a size of 228.2 MB, whereas the TF Lite version has a size of 212.33 MB, which is still very large when we compare to the apps which are shipped on mobile devices. So yeah, MobileNet V2 was chosen as the model that will be shipped with the phones. These are our mobile screens where we had the UI in this way. The farmer can enter the phone number. He will get an OTP. The OTP, when he enters the OTP, he'll be signed in the default weather screen, which will show the weather each and every day. When he clicks on the camera button, it takes him to the image gallery where he can choose the image. And as we can see, we can also we can go to the gallery button to choose the image, or it will open up a camera screen to take the image directly. Once he chooses the image, a preview screen is shown where he can preview his image if it is correct or wrong. If it is wrong, he can click on cancel button. He'll go back to the home screen. If he clicks on right, the image is then sent back to the model for analysis, and then the model recognizes the plant disease, depending on which we will query the database and show the result in this way, where we will actually show the top three results that we find depending upon the confidence score. We still has the human layer where the farmer still has the right to choose the correct thing, because even after because there can be cases where we can have results with 99% accuracy and 98% accuracy. In those cases we still need a human layer to identify the correct diseases. So basically the farmer can click on the cards which is shown, it will open up and it will show the symptoms and remedy and even preventive measures if they exist. So, conclusion. Even though we have shipped an app which can easily identify plant diseases, there are still several factors that we haven't um, tackled yet or considered yet. There are certain problems which we still have to tackle, which is the language barrier. Basically, if we consider India, not every farmer can speak Indian English language, and most of the farmers can only speak one or two languages, which is one either their local language or two Hindi. So shipping an app which can internationalize language is very important. From the rise of vernacular apps, every app that pertains to Indian farmers must support various Indian languages, which has to be added to our app, as I mentioned earlier. Also, not every farmer can type properly, because even the keyboard is in English, right? Even though we convert the keyboard to Hindi, it does not give that good UI experience. So a support for voice interaction is very much important. Support for voice interaction is a big breakthrough in this technology, is already getting matured enough to provide useful resources such as Google Assistant, Siri, Amazon, Alexa. And adding this will greatly enhance the user experience, and it will make the app more accessible to all farmers across the country. The current implementation analysis of plant image to classify it among a disease to add more accuracy to the classification. Few questions can be asked to farmers as such as the kind of plant, visible appearance of the plant disease. This will greatly enhance the classification and detection of the model, since now the model can be trained on various other features which will be given as input by the human. Our future work, due to the evolution of automation technology, the whole process of plant disease detection can be automated using drones. So we can make our app very highly scalable, where the farmers doesn't even have to go to the fields and click the images. What we can do is we can start a whole system where we can fly drones over their fields, and the drones will be able to capture the field images. And based on those field images, we can detect if uh, basically if the field has certain kind of disease or not, and we can also geotag those kind of fields, so we have a proper data set containing the affected regions and the non-affected regions. Keeping this in mind, the mobile application also provides should also provide a geotag service which can be leveraged at later part of the implementation of the project to keep the track of affected areas of the field. Yes, as I mentioned, the drone in future we can use drones to geotag the field, but even the mobile application should have such a process. If the farmer tries to detect the plant diseases that he might have, he should be able to geotag those certain we should be able to geotag those certain fields so that we can have a proper data set of which regions are being affected by what kind of diseases, so that we could enhance our study further and know what are the particular conditions in those particular areas which cause certain diseases. So these are our references. Our major reference was using the large scale hierarchical image dataset, which was our village dataset. And we also took a deep dive into UG's open access repository of images on plant health to enable development of mobile disease diagnosis. We also took help of certain open source websites which are like tutorialspoint.com, Geek for Geeks, and TensorFlow, for various challenges that we might have faced during the development of the app and training of the model. Thank you.